So I have a lot of topics I'd like to cover today. I wanted to try and put in context several of the projects that are going on in my lab related to VQA and the types of problems the previous speaker was just referring to. And so I apologize if I end up going a little too fast on some of these, but the good news is there's other presentations later in the week that you can see. So I'll briefly mention some of our work, the background work on captioning, and fortunately we don't call it referring expressions, so I won't get into an argument with anyone. We've been calling it grounding or natural language object retrieval, and I'll tell you a little bit about that. And attention, and then I assume everyone saw the earlier talk on the multimodal compact bilinear model, and I'll step through that very briefly, and then hopefully I'll have enough time to focus on what I think are the harder challenges for the future, and that relates to what we've been calling compositionality. And there's two different types of compositionality with two different talks in the main conference that I'll explain in some detail, and then maybe have a few moments discussing even beyond question answering towards explanations. So, many of us have been excited about the idea of combining language and vision models and networks and the success of captioning that we all saw last year and the year before. And as we saw in the great work from Google in the previous talk, these models can also be used for visual grounding. So here we're only focusing on half of the problem that they spoke about, just the version of the problem where you have an image and a sentence or a fragment, and you'd like to figure out where in the image does this fragment refer to. We've been calling this natural language object retrieval, following on earlier work that Sergio Guadarrama and others at Berkeley in the past have worked on, where you take the I don't want to say referring expression, but the expression that's referring to something in the image, and essentially score it with various regions. You can find the highest probability score, and that starts to be a good model to try and figure out which object is being referred to. So you can say the man on the far right and get that, the left guy and get that, the cyclist and get the person in the middle. So this model is going to be presented in Ronghang Hu's talk on Thursday morning. And indeed, a discriminatively trained model does outperform the more simply trained model, as Kevin discussed earlier. Our version of that is available in an archive from Anna Rohrbach and colleagues. So I just wanted to mention sort of the first step towards visual question answering is to be able to caption and be able to ground. And indeed, the early work from Mario Fritz and his colleagues showed that these models could generate directly generate answers to questions, as their early work demonstrated. But there's a key need to include spatial reference and this kind of grounding. And in the context of question answering, there's been a few early works in attention modeling that many of you are familiar with. I'll just highlight the model from Kate Senko's group, which influenced our work, where they directly applied the memory network architecture from Facebook to grounding the VQA questions, and started to get this notion of a spatial attention map that could refer to what in the image needed to be extracted. And as you'll see, our model makes use of this kind of architecture, but with an even more fine-grained attention map. So this leads me to talk about the work that was already presented earlier today that won the Real Image Challenge. Very happy to be working with Akira and Marcus, who led the effort, and Dong-Huk and Daylin, who are probably still here. And Anna and myself helped out a bit. So I think I assume everyone saw that talk. Raise your hand if you saw the talk. Well, about half. So in a very small nutshell, the idea is to address how do we fuse the two. So in the end, we're going to be fusing three different things. We've got lexical content, we've got visual content, we've got lexical content, and we have spatial content. And so we'd like to fuse all three of these things. Let's start just fusing the visual content, the visual semantic content, and the lexical content, and finding out which words are going to relate to which visual concepts to try and answer questions. And if we go to sort of simple baseline methods of concatenation, they've gotten us part of the way there, but they don't allow the full set of interactions between pairwise components in a model. You could have element-wise multiplication, but that also misses the boat because you'd have to have perfect alignment between the two spaces. And indeed, the idea of looking at the outer product or bilinear pooling model as was represented from Subhranshu Maji's group at last ICCV, this starts to get a model that's shown to be powerful, at least in fine-grained visual recognition. And so we had the intuition and the good fortune to find out that it also does work for this kind of multimodal fusion as well. So we applied this in a multimodal fashion, not just looking at two different visual descriptors as in the previous work, but in a visual and text model. The literal application of the bilinear pooling is prohibitively space expensive, and so we also had the good fortune to be able to leverage other work that's recently been released in my lab that we call compact bilinear pooling, which applies ideas from sketching and hashing to this bilinear pooling model. And that's a paper by Yang Gao, Oscar Bejabum, Ning Zhang, and myself, and that I think is on Monday afternoon as a poster here at CVPR. So this is just a current CVPR paper that we're applying and is now also the mechanism for the multimodal model in this in the work presented in this workshop. So to do this efficiently, we leverage, or the ideas in the Yang's paper are to apply a sketching approach using a technique called the Kout sketch from Charikar's lab, and an observation that this can be approximated using convolution, and the convolution can be approximated with FFTs. So for details on all that, please go see Yang's poster. And further, that's the mechanism for combining visual semantics and words. And on top of that, as I mentioned, you need to focus on what you'd like to describe, or focus on what needs to be attended to answer questions in the VQA challenge. So the spatial attention model the previous authors had shown valuable turned out to be valuable here as well. And I think as the results show, somehow the use of this compact bilinear feature really let the attention model be even more powerful. So it was the combination of MCB and spatial attention that seemed to really outperform. So you can look for where the yellow food, and there were previous examples in Marcus's talk that are even better than the one I had here. The results speak for themselves. The MCB alone got this number, but with attention, it got that number, and then with the other standard tricks of ensembling and data augmentation, it ultimately won the challenge. So, what do I have, 10 minutes left? 5 minutes left, okay, because this is the more fun part. That's where we got to that's where we began, that's where the state of the art is. I think that summarizes what leads to the strongest performance right now on the VQA challenge, but I think there's still much more to be done, and there's still many more opportunities than accomplishments, I guess is one way to phrase it. And I think compositionality is one point that we're pushing on in particular this year. And you can think perhaps of 3 levels of compositionality. One level of compositionality is that the training set literally is sufficient to, and it contains all of the variability necessary for all the types of captions that you'd like to express, and that's of course somewhat limited. Another layer is perhaps a lexical layer, or at least we can use terms or noun phrases that are outside of our multimodal training set. And ultimately, we'd like to have full compositionality without any qualifier, or maybe we call it structural compositionality. So I first talk about this idea of lexical compositionality, and this is the paper that Lisa Hendricks will present as the first talk in tomorrow morning's session. So I'll just preview this briefly for you now. We call it deep compositional captioning. This is compositional at the sense that it can use new terms interchangeably as it's captioning a scene, and obviously this is also very useful for natural language object retrieval or reference or whatever the best term is for that. Because we know we can caption things, but that's great. The captions, this is what the training data looked like. So, nearest neighbor, as many people pointed out, would have worked pretty well for these models. Nearest neighbor doesn't work very well for this image for the standard data sets. This is not a bear, but both of the models would call it a bear and say that it's charging through the grass. It's great that it actually knows how to speak about this image that it doesn't actually know about, but we'd like to actually be able to call it what it is, an anteater, and there's plenty of visual evidence on the internet about what anteaters look like. So that leads to the model that Lisa developed called the deep compositional captioner, and essentially it's a way to augment the multimodal vision and language models to also naturally incorporate sources of unpaired data. There's a large amount of unpaired text on the web, there's a large amount of unpaired image data on the web, or it's paired, but it's paired with just single words. It's not paired with full captions. And so that's the main idea, and in a nutshell, it learns to train the individual modules and then learns essentially to do this neural grafting step to find the nearest proxy term. If I learn what an anteater or an impala looks like, I still need to figure out how do I talk about anteaters and impalas, and for that it finds the sort of nearest I don't want to use the word grounding term, and transfers the weights that correspond to language use for that term. So you can learn more about that tomorrow morning. But it gives you results like this, where it can speak about nouns that wouldn't have otherwise been in the data set, and the previous models would have sounded a little bit silly, calling it a bird or a baby or something like that. And I should mention, not only is there the work that's being reported tomorrow morning, but there's also a follow-up work that was just released on arXiv called the Novel Object Captioner, which further improves on this model. And you can look for that. It's a collaboration with Shuba and colleagues from the University of Texas and Ray Mooney's group. So that's what I was calling lexical compositionality, but that's just scratching the surface of a compositional model, and that leads me to the next thing that I'd like to speak about, which is the last talk that will be in the morning session tomorrow morning, and that's the work of Jacob Andreas and Dan Klein and Marcus and myself at Berkeley, which is jointly reported in 2 papers, the paper tomorrow called Neural Module Networks, and also a paper that was technically a follow-up paper that won a Best Paper Prize at NACL called Learning to Compose Neural Networks for Question Answering. And this really tries to take a clean slate, design approach to how would we have a compositional neural model that can answer complex questions about, semantic grounding in images, which both has a structural flavor that follows traditional NLP models, but also directly leverages deep architectures for especially the visual aspects of grounding. And the sort of overview in one sentence is, or one slide, is an architecture that compiles a new neural architecture on the fly for each sentence, corresponding to the parse structure of the sentence, where the semantic grounding of each element in that parse structure can be specialized to the actual semantics of the sentence. So it combines both compositionality, like we would have in traditional NLP models from semantic parsing, with the revolution in deep learning and representation learning that we have in computer vision. So you start off with the sentence, you can roughly parse it using existing techniques, and get a semantic parse that might look like this. And each of these constituent elements would then be grounded with parameters being tied. What it means to be a circle in this sentence is the same as what it means to be a circle in this sentence. And when you get a visual scene as input to these sentences, they are going through the same tied weights. So every sentence in the corpus is instantiated as this type of structure, and all of the weights are shared across each of them. And it may look complicated, but the learning is still straightforward given this architecture. So this model can instantiate sentences for VQA, and also you can implicitly see where the attention is going after you've looked for wearing. The word wearing would give you a spatial mask that is revealed. The sheep's ear would give you a spatial mask that would reveal tag. And you can also ask very complicated geometric questions about geometric scenes that have complicated forms of compositionality. And the model works very well on those. And so the punchline is this model just does normally well in the VQA challenge. This was done independently of the MCV work, so this model doesn't necessarily have the best numbers right now, but it kind of clearly has competence in this type of sort of synthetic data, which is almost a toy data set from the perspective of computer vision. But if you can't solve this toy data set, it seems like you aren't really handling compositional challenges. So I think that in the future we should hope for real data sets that have the kind of rich compositionality that these toy data sets have. And for now, we're still left just evaluating the data sets that we have. So on this type of shapes data set, our model clearly outperforms all the previous work, and it's going to be future work to combine the two different VQA models that are both in the group right now. So in 1 minute perhaps that I have left, I just want to maybe go beyond VQA a little bit and talk about visual explanations. I think, being able to answer questions or having intelligent systems that can report things to people in environments is very important. But often people feel that if they can't query the system and ask it why it thinks something is true, it can lead to a system that isn't trusted by users, or users aren't sure what they feel about it. And so we've started to try and define a new class of problems that we call visual explanations, which are both relevant to an image and relevant to a decision or description that's been made about an image. And I think at first glance it seems very challenging to do this, but you can directly use the types of machinery that we've used for captioning to also generate textual rationales or explanations of why something is being made, some decisions being made. Here we have a joint model, which is a fine-grained visual recognition system, and a description of why experts in the past would have thought this was the decision to be taken on this image. And so I can tell you more about that if you wish, or you can look at our archive called Generating Visual Explanations. And Lisa Hendricks is also the first author on that. So with that, I think I'm mostly in time, and I will close by just listing the papers that I've referred to and point out where some of the presentations for them will be.